Hello everyone, welcome back to Aero Hub and welcome to the series of lectures in Gate Aerospace, and we were solving numerical problems of structural dynamics in the previous part, and we will continue to solve the numerical problems in structural dynamics. As you can see the question, this question was asked in Gate 2007. The equation of motion of a vibrating rod is given by dou square u by dou x square is equal to 1 by c square into dou square u by dou t square. Here u is the displacement, t is the time, and this is the equation of motion for a rod or a bar. And we have two questions. The first question is the boundary condition needed for a rod fixed at the root, that is x is equal to 0, and free at the tip, that is x is equal to L. Okay, so we have to find out the boundary conditions. Okay, and you can see the options. Option A, u of x is equal to 0 is 0, and dou u by dou x, that is nothing but the strain acting at the tip, it is equal to 0. Okay, and option B, u of x is equal to L is equal to 0. Okay, that means the displacement at the tip is 0 and the displacement at the tip, the strain at the tip is also equal to 0. Okay, and option C, u of x is equal to 0 is equal to 0, that is the displacement at the root is equal to 0 and the displacement at the tip is also equal to 0. Okay, and dou u by dou x of x is equal to 0, that is nothing but the strain at the root and strain at the tip is equal to 0. Okay, and we have the condition fixed at the root, that means the displacement should be 0 at the root. So option A and option B is having the displacement 0 at the root and free at the tip. Okay, when the tip is at free condition, the strain, that is dou u by dou x, should be equal to 0. That is, when the strain is equal to 0, that will be the condition for the tip. Okay, but displacement is there at the tip, but the strain will be equal to 0. Okay, so if you are checking out the option between option A and option C, we can see in option C the displacement at the tip is also equal to 0. So this option cannot be satisfying the condition. Okay, we are having a fixed structure, we are having a rod in this manner. This is the rod of circular cross section, and the displacement at the root will be equal to 0 and we will be having some amount of displacement at the tip. Okay, so this option C is also not valid, so the answer is option A. Okay, the answer is option A. We have displacement is equal to 0 at the root and we have the strain at the tip, that is equal to 0 at the tip. Okay, and you have to remember that when the strain at the tip is equal to 0, it doesn't mean that the displacement at the tip is equal to 0. There will be a displacement at the tip, but the strain will be equal to 0 for a vibrating rod. Okay, this is the condition. And the next question, the natural frequency omega of fixed free rod can be obtained using, we have options. Option A, cos of omega L by C is equal to 0. Option B, sine of omega L by C is equal to 0. Option C, cos omega C by L is equal to 0, and option D, cos omega by C is equal to 0. Okay, to solve this problem we have to use the equation of motion and the solution for the equation of motion. Okay, so we have the, so I will write the solution. We have the equation of motion, that is dou square u by dou x square is equal to c square into dou square u by dou x square. This dou square t square. Okay, dou square t square by is dou square u by dou t square is equal to c square into dou square u by dou x square. Okay, and here c square is equal to the area, cross-sectional area, into Young's modulus divided by the mass. This is the value of c square. Okay, this is about the governing equation or equation of motion of a vibrating rod, and I'll put this as equation number 1. And the general solution for the equation is given by, the general solution is given by u is equal to a sine omega t plus b cos omega t into c sine omega by c into x plus d cos omega by c into x. This is the general solution for a vibrating rod or a vibrating bar. A sin omega t plus b cos omega t into c sin omega by c into x plus d cos omega by c into x. Okay, so how do you find out the natural frequencies? Okay, we have the boundary condition fixed and free end. Okay, fixed and free. Okay, so you substitute the boundary condition, that is u of x is equal to 0 will be equal to 0 and dou u by dou x at x is equal to L is equal to 0. These are the boundary condition. So you substitute the value of boundary condition in the general solution, then we can obtain the value of omega. We can obtain the value of, we are not obtaining the value of omega, we are obtaining the condition for omega. Okay. Now I will substitute the value of boundary condition in the general solution. So we'll apply the first boundary condition, that is u of x is equal to 0 is equal to 0. Okay, so u is equal to 0 is equal to a sin omega t plus b cos omega t. Okay, this a sin omega t plus b cos omega t will not be equal to 0 because that is a fundamental equation of wave. It won't be equal to 0, so this part will be equal to 0. Okay, into, I will substitute the value of x is equal to 0, so it will be c into sine x is equal to sine of 0 plus d, this is cos, okay, not sine, d cos of 0. Okay, we know that this value, this entire value should be equal to 0. Okay, and we have cos 0. Cos 0 will be equal to 1 and sine 0 is equal to 0. So I can write d should be equal to 0 to satisfy c sine 0, this part as 0. Okay, to satisfy this entire part as 0, the value of d should be equal to 0. Okay, that is the, so we got the first value by applying the boundary condition number 1, d is equal to 0. Okay, we'll apply the second boundary condition, that is at the free end, that is x is equal to L, dou u by dou x is equal to 0. Okay, that is the strain at the tip is equal to 0, and I'll again write the value of u is equal to a sin omega t plus b cos omega t into multiply by c of sin omega by c into x plus d cos omega by c into x. Okay, and the value of d is 0 here, so this value is 0. Okay, now dou u by dou x will be equal to, I am not differentiating this part, it's always a constant, a sin omega t plus b cos omega t into, I will differentiate this part. Okay, so that will be equal to multiplying this equation by the differentiation of this part. I'll be C into omega by C into cos omega by C into x, and for x the value will be equal to L. Okay, that is we at the tip the strain is equal to 0, so it will be I'll put as L. Okay, so this entire equation should be equal to 0 because dou u by dou x is nothing but the strain at the tip. Okay, and this equation is the fundamental equation that cannot be equal to 0, so I can write C of omega by C into cos omega by C into L is equal to 0. Okay, and C is nothing but what is C square? C square is A into E by mass, and omega is also having certain value, so this term cannot be equal to 0. Okay, so I can write cos omega by C into L should be equal to 0, and this is the satisfying condition to obtain the value of natural frequency, and the option is option A. Okay, you can see the option A will be the answer. Okay, so that's all about this short lecture. We will see you in the next lecture. Thank you for listening. Take care.